Good morning, students. Yesterday we started inner product spaces, and today we will do the examples of Hilbert space. Hilbert space means complete inner product space. Complete inner product space means that should be complete in the metric defined by the inner product. So firstly, in order to prove inner product space, firstly you will define inner product. Then after that you will define a metric by using that inner product, and then you will prove that the vector space is complete in that metric. In that case, the vector space will become complete inner product space. So that will be called Hilbert space. Today we will do the various examples of Hilbert space. So the first example is Euclidean space. Euclidean space means n-dimensional space of real numbers. We will prove that this n-dimensional space of real numbers is a Hilbert space. In Hilbert space, which is n-dimensional space of real numbers, in order to prove this, we will define inner product. So to define inner product in this space, let us take two elements from Rn. We have taken x and y because x and y are n-dimensional. So we will take their coordinates and coordinates. We have taken the coordinates of x as xi1, xi2 and so on xin, and the coordinates of y eta1, eta2, eta3 up to eta n. We have defined the inner product by the coordinate wise multiplication, means inner product of x and y is equal to exile1 eta1 plus exile2 eta2 and so on, exile n eta n. In this way we have defined the product. Now we'll prove that this product defined by us is an inner product. So we will verify the properties of inner product. So the first property of inner product is linearity with respect to addition in the first variable. Means we are to prove that if we take three elements x, y and z from Rn, then inner product of x plus y with z is equal to inner product of x with z plus inner product of y with z. So let us consider three elements x, y and z. X is this element, y is this element, and z is the element having the coordinates xi1, xi2, xi3 and xin. Now let us find inner product of x plus y with z. Now substituting the value x plus y means coordinate wise addition of these coordinates, means exile 1 plus eta 1, exile 2 plus eta 2, exile 3 plus eta 3 and so on, exile n plus eta n. Now this is x plus y and z is this. So by using the definition of inner product which we have defined, inner product of x with y is equal to exile 1 eta 1 plus exile 2 eta 2 and so on, exile n eta n. So using this definition here, we get inner product of x plus y with z is equal to the sum of the product of the coordinates of this vector and this vector. So these are given by this. Now opening the multiplication here and separating the summation, so we get summation exile I psi I plus summation eta I psi I. Now by definition, this is the inner product of x with z and this is inner product of y with z. So we have proved the first property of the inner product. Now second property, we are to prove inner product of alpha x with y is equal to alpha into inner product of x with y. So in order to prove this, let us find inner product of alpha x with y. Now again, by using the definition of inner product, the sum of the products of the coordinates of this vector and this vector. So that will become this. Now taking alpha out of the summation, we get alpha into summation exile I eta I. Now this is again inner product of x with y. Now the third property, conjugate symmetry, means inner product of x with y is equal to the conjugate of inner product of y with x. So let us start from inner product of x with y. Now by definition of inner product, this is the sum of product of the coordinates of this and coordinates of this. So this will become summation exile I eta I. Now this can further be written as summation eta I into exile I conjugate. Now because Rn is a vector space over the set of real numbers, so if we take x and y, if we take x having the coordinates x1, x2, x3 up to xn. X is n dimensional, and here xi, eta I, these are real numbers, so their product will also be real, means summation xi, eta I, that is real, so the conjugate of real number will be same as itself. So we can say inner product of x and y is real. So from this equation, summation eta I xi conjugate will be same as itself. So inner product of x and y will be same as inner product of y with x conjugate. Now next property, fourth property, inner product is non-negative and inner product is 0 if and only if the element itself is 0. Now inner product of x with x. So by definition, that will be the sum of the product of coordinates of x with itself. The coordinates of x are exile1, exile2, exile3 up to exile n. So inner product of x with x will be summation xi square. Now because xi square are non-negative quantities, so this will be greater than equal to 0. Now let us take this inner product is equal to 0. If we take this inner product is equal to 0, we get summation xi square is equal to 0. Now the sum of non-negative quantities are 0. It means these quantities will be individually 0. So each xi will be 0 for every I varying from 1 to n. Because xi are the components of x, each component of x is 0. So we can say that x is 0 vector. So we have proved inner product is 0 if and only if the element itself is 0. So we have verified all the properties for the inner product. Till here we have proved that Rn is an inner product space. Now to make it Hilbert space, we will have to prove that it is complete in the metric defined by using the inner product. Now let us define a metric by using the inner product. Now in order to do that, now we know that norm is square root of inner product of x with itself. Now inner product with itself by using the definition of inner product as we have defined already in this example. So that is square root of summation xi square. Now from this norm we can define a metric. So let us define a metric denoted by d of xy is equal to norm of x minus y. Now by using this definition, this will become summation xi minus meta I square and its under root. So this we have defined a metric, and with this metric, this Rn is complete metric space. So we have obtained complete metric space. So Rn is Hilbert space. So this was the first example. Now next example is also the same, that is only the basic difference between the two is here we are using the n dimensional space of complex numbers, which is called unitary space. The basic difference between the two is only that here inner product of x and y, that is defined by summation xi into eta I conjugate. This is the basic difference between the two. Here x and y we have taken from the space Cn and we have defined the inner product of x and y in this way. Now again in the previous example, firstly we will prove that this is inner product space. So firstly we will prove that this product defined by us, that is inner product. So in order to prove that this is inner product, we will prove the properties. The first property is inner product of x plus y with z. Now inner product of x plus y with z, we have to prove this is equal to inner product of x with z plus inner product of y with z. So to prove this, let us take three elements x, y, z. Now inner product of x plus y with z, use the definition of inner product again. So this is given by summation, the coordinates of x plus y, these are xi plus eta I, and coordinates of z are psi I. By using the definition of inner product and separating the summations, we get the first property, inner product of x plus y with z is equal to inner product of x with z plus inner product of y with z. Second property, inner product of alpha x with y is equal to alpha into inner product of x with y. So let us start inner product of alpha x with y. Now coordinates of alpha x are alpha into xi. Using the definition of inner product, this is summation alpha xi into eta I conjugate. Alpha can be taken outside of the summation. Inside, this will become inner product of X with Y. So we have proved the second property. Now the third property is conjugate symmetry. Inner product of X with Y is equal to the conjugate of inner product of Y with X. So let us take inner product of X with Y. Using the definition, this is summation xi into eta conjugate. Now this term can be written again in this form. Now this can further be written in the form summation, because these numbers are commutative. So this can be written as summation eta into xi conjugate whole conjugate. This is inner product of Y with X conjugate. So we have proved the third property. The fourth property is non-negativity. Inner product of X with X is greater than equal to 0, and inner product is 0 if and only if the element itself is 0. Let us take inner product of X with X. Now by definition, this is summation xi square, which is non-negative, and this is 0 if and only if each xi square is 0. So we get xi is equal to 0 for every I, so X will be 0. So we have proved that in this product defined by us, that is inner product, and the space becomes inner product space. Now to prove it is Hilbert space, we will prove that it is complete in the metric defined by the inner product. Now let us define a metric. Now again, by definition of norm is the square root of inner product of X with itself. So by using the definition of inner product, which we have defined already, by using this definition, this is summation xi square under root. Now let us define the metric. Distance between X and Y is equal to X minus Y norm. So X minus Y norm means square root of inner product of X minus Y with itself. Now by using this definition, this will become summation xi minus eta mod square under root. Under this metric, the space Cn, that is complete. So we have proved Cn is complete metric space, and this complete metric space, that is called Hilbert space. Next space is L2 space. L2 space is called Hilbert sequence space. In the Hilbert sequence space, we define the inner product of X and Y, where X is the sequence given by xi, Y is the sequence given by eta I. So this is given by the sum of product of the coordinates of X and Y. Here summation varies from 1 to infinity. Firstly, we will prove that this product is inner product. So in order to prove this, we will again verify the properties. Inner product of X plus Y with Z. So inner product of X plus Y with Z, use the definition of inner product and separate the summations here. You will again get inner product of X plus Y with Z will be same as inner product of X with Z plus inner product of Y with Z. Second property, inner product of alpha X with Y. Now these are the coordinates alpha X, and coordinates of Y are psi I. So by using the definition and taking alpha outside of the summation, this term will become inner product of X with Y. Next, conjugate symmetry. Inner product of X with Y. This is summation xi into eta conjugate. Now this term can also be written in this form, and from here again this can further be written in the form summation eta into xi conjugate and again conjugate, which is the conjugate of inner product of Y with X. Last property, inner product of X with X. Now inner product of X with X, this is summation xi into xi conjugate, where I varies from 1 to infinity. Now this is xi mod square. Now because these are non-negative quantities, so that will be greater than equal to 0. Next, if inner product is 0, this term will be 0, and because these are non-negative quantities, so each term will be separately 0. So each xi will be 0. So coordinates of X are 0. So X will be 0. So till here we have proved that L2 is inner product space. Now we define the metric. In order to define the metric, let us firstly define norm. By using the inner product, norm is the square root of summation xi mod square. With this norm on L2, the space, that is the complete metric space. So L2 is complete. So we can say that L2 is Hilbert space. So these were the various examples of the Hilbert spaces, and tomorrow we will do the examples of the spaces which are not the Hilbert space. Thank you.